All right, welcome back. My name is Brian Waddy, and today we're going to look at characteristics of polynomial functions. So we're going to consider a couple different cases of different types of functions based on degree and see if we can figure out some relationships between them. So let's look at, let's see, we'll start with, well actually, I guess I could technically have a constant, but we'll start with linear, which is something like a y equals x, right? Any first degree function. Then we'll look at quadratic. So let's say I have the function y equals, actually maybe I'll use the function notations, get us used to that. F of x equals, say, x squared minus 2 would be an example of that. Let's see, and then we'll try to look at a cubic, which would be like y equals x cubed minus x squared plus x minus 2 or something like that, right? So a third degree function, and we'll look at a quartic as well. And technically I could keep going, but let's just say I've got y equals x to the fourth minus x cubed plus x squared minus x plus 1. Let's do something like that. So what I want to do is just draw kind of what a basic graph would be for each of these, and then based off of these graphs try to determine what relationships or characteristics each of them would have. So linear function y equals x looks something like that, right? So there's no curves in a linear function, linear as in like line, right? So we've seen that before, we're used to those. Quadratics we know are represented by parabolas, and we've got a lot of experience with those. You might even know that this one has a y-intercept at -2. You could probably find the vertex, you could probably find where the x-intercepts are, and all sorts of things like that. And this would also, you'd be able to know that it's opening upwards and so on and so forth, and it's a regularly shaped parabola. For this third degree function, this is something you're not used to. Now this is probably not what this function actually looks like, but let's say it looks like this, where it's kind of got this two little bends in it, and it's heading off in opposite directions infinitely. And then this fourth degree function will look something like this. Actually, all right, so here's our four basic polynomial functions. They can keep going. We actually can have functions with way more bends the higher the degree they get. But let's first look at x-intercepts. All right, so for x-intercepts, for my first degree function, the greatest number of x-intercepts it could have is 1, right? Even if I had a line over here or a line like this, it could have at most one x-intercept. Technically it's possible I could have a horizontal line that's linear and it never crosses the x-axis, so it could have no x-intercepts. But so for x-intercepts, this has at most 1, right? So one x-intercept, let's say. For a quadratic function, you guys might remember the discriminant, that we were able to use that to determine the number of roots or the nature of the roots or the number of x-intercepts or zeros, whichever you'd want to call them. And for quadratics, I had a second degree and I had at most 2 x-intercepts. And remember, we could have also had parabolas like this that had no x-intercepts, where it never crosses the x-axis. I also was able to have a parabola that maybe just ricochets. Oh, that's a terrible case, but let's say it was tangent to the x-axis. If the vertex was on the x-axis, it's possible to have just 1. But at most, I can't draw a horizontal line that hits this parabola any more times than twice, right? So quadratic, second degree, has at most 2 x-intercepts. Looking at the cubic function, so third degree, notice that it can have as many as 3 x-intercepts, right? Now, it is technically possible that I could have 2, right? If I had it come down and, say, hit tangent right there, I could have 1 and 2. It is possible even to have it hit only once, right? If I have it hit right there. And actually, an interesting thing about a cubic is that I can't have no solution. I can't have no x-intercepts. No matter what, it's going to cross at some point. I can't avoid it. And part of it's going to relate to this end behavior we'll talk about a little bit later. So this one has 3, 2, or 1 x-intercepts, right? But at most 3. Right now we're just interested in the greatest number. And then notice for 4th degree, the number of x-intercepts could be 1, 2, 3, and 4, right? With the number of bends it has. I could draw a line like this that hits twice. I could draw a line like this that hits 3 times if it was tangent at one of those points. And it's even possible to have none for this. But one of the things I want you to realize is that x-intercepts, we'll say max number of x-intercepts is equal to the degree. Right? And just like in the parabola, sometimes you could have less, right, depending on where it crosses, or if it doesn't cross at all, or if its vertex is on it. But the max number of x-intercepts is equal to the degree. So that's one of the first relationships I want you to notice. Let's see, the next relationship I'd like us to look at is the number of bends that the function has, or the number of, I could refer to these as local extrema, or relative max and mins, right? Or relative extrema, I think is actually the way it's usually called. But the number of bends, notice that this linear function, it's a line, there's no maximum point. There's no like height or lowest point on the graph. So this has 0 bends, right? So 0 bends. Notice the 2nd degree function has our vertex, right? Which is 1 bend in the graph, so 1 bend. And it's not possible to have a parabola that has more than 1 bend. Even if it opened downwards, it would still have that 1 change in direction, right? For our cubic function, notice this one actually has 2 bends, right? So it changes direction twice. So this one will have a max and a min relatively, because obviously this keeps going up forever, so the max is technically infinity. But it has 2 bends in the graph. And for the quartic, notice it has 1, 2, 3 bends at most that occur in the graph. All right, so this one has 3 bends. So as far as the number of bends, the max number of bends, I'll call them bends. I might say relative extrema, or we can even call them, sometimes I'll say local max or mins, is 1 less, right? Notice, let's see what happened here. When the degree was 1, I had 0. When the degree was 2, I had 1. When the degree was 3, I had 2. When it was 4, I had 3. So it appears to be 1 less than the degree of the polynomial. Right? So that's our number of bends in the function. All right, so we're able to figure that out. So that's another characteristic of our graph. Let's see. I think the other thing I'd want to talk about is, let's see, we talked about x-intercepts, we talked about the number of bends. We should talk about end behavior. So notice for this linear function, our end behavior, this as x goes to infinity, right? As x goes to infinity, it appears that y is going to infinity as well. All right? So as x gets bigger, right, here's the positive x, y is getting bigger for this. And as x gets smaller, the further I head to the left on my function, it appears as though y is also getting smaller. All right, so for linear functions, at least when there's a positive coefficient, We'll talk about that later. Positive leading coefficient. The end behavior will be positive, positive, and negative, negative. All right. Maybe you could find different ways to describe this, but when I'm talking about end behavior, I'm talking about for the very large values of x, what's happening with y. Okay. So this is when x is positive, y is positive. When x is negative, y is negative. And also one of the things I want to point out is that these are going in opposite directions. Notice that when y is going positive over here, it's going negative over here. Whereas the end behavior here, it appears as though the end behavior is, it's going to positive y for both of these, right? At least when we have a positive leading coefficient. Remember how we'd have an upside down parabola whenever a was negative? Well, then our end behavior would have been down and down, but notice that they're actually going to be pointing in the same direction. All right? So that's one thing that I want you to notice. So there's kind of two things we're talking about here, is where is it actually going based off of the leading coefficient and its degree. All right? So that'll actually give us a general idea of what's happening to the function on the outer parts of it, not necessarily how many bends it might have or anything like that, but we know that for the very extreme values, this is what's occurring. All right, so it appears a positive, positive, no matter where x is going, right? When x is going positive, y is going positive. When x is going negative, y is going positive, right? And part of that relates, remember if I plug in a negative number here, negative 2 squared is a positive 4. Negative 100 squared is a positive number, right? So that makes sense that these negative values are getting positive as a result in the end there. Look at the end behavior here for the third degree. It appears to be similar end behavior to the linear function, right? For a positive leading coefficient, when x goes positive, y goes positive. And when x goes negative, when I go to the left on this function, the y values are getting smaller and smaller, right? So it has the opposite end behavior again, where it's pointing in different directions, and it's following the path of the x in some ways. And then the end behavior for the quartic, it appears as though it's similar to the quadratic, right? So here's another even function, even degree, right? 2 and 4 are both even numbers, 1 and 3 are both odd. It turns out that it's similar to this, right? And this is once again related to that even exponent, right? If I plug in a negative number here, negative 2 to the 4th is going to be positive 16 because it's being raised to that even exponent. So I actually end up having that same relationship as I did here, where it heads to positive y, at least as long as I have a positive leading coefficient. And actually there is a way that I could have an upside down kind of w here the moment that I get a negative leading coefficient, but notice that they would actually be heading in the same direction once again. So let's see if we can summarize this. This I might make a little table. So let's see, for end behavior. All right, let's talk about degree. We'll talk about leading coefficient. And then we'll talk about when x is positive. Actually, maybe... And then I'll just describe the end behavior. I'll have two relationships for each of these, for when x is positive and when x is negative. All right, so we'll make this little chart. So when I had an odd degree function with a positive leading coefficient, all right, so that was like our linear and our cubic here. What did we have? We had when x goes to positive infinity, we knew that y went to positive infinity, right? And when x went to negative infinity, we knew that y went to negative infinity, right? So what I'm saying here is when we went to the right, the y was getting bigger. When we went to the left, the y was getting smaller. And that was true for either of these odd degree functions. Now, what do you think happens when I have an odd function with a negative coefficient? Well, just like the parabola, how it would flip upside down, let's think about what happens to this kind of S-bend. If I flipped this, all right, it would just switch the end behavior, but they'd still be pointing in opposite directions. Okay? So odd negative, this time when x goes to positive infinity, y would go to negative infinity. So it just flips it. And when x goes to negative infinity, y would go to positive infinity. All right? So they end up flipping the direction. Now the even functions were the same either way, right? So even positive, that's like our upward opening parabola. When x went positive infinity, y was positive. And when x went negative, y was still going positive. Remember that it opened in the same direction for both cases, right? So both of these were going upwards no matter which direction, left or right, we were going. And lastly, we've got the even and negative. Right, so that would be like our upside down parabola, where whichever way x is going, it's going down, right? So y is going negative for both of these cases. So I don't necessarily recommend that you memorize this little table here. I think it would probably make more sense just to kind of visually understand. Actually, even if the two things that you think about for end behavior were the linear and the quadratic, we're pretty familiar with a slope that's negative, right? And an upside down parabola as well. So you'd probably be okay kind of just visualizing those pictures in your mind when you think about the end behavior. And technically it's possible that you could calculate the end behavior by just plugging in really big numbers for x or really large negative numbers for x. But that would be a lot of unnecessary work. But it would still kind of give you the same result. You'd realize, oh, okay, y is going positive here or y is going negative there. All right, so that, I believe, is most of the characteristics of parabolas that I wanted us to know about. And that should have us pretty well set up. So that way, if I describe, actually, let's do an example. Might as well end on an example. So if I said sketch a graph of, let's say I have h of x equals x cubed plus 3x minus 1. Well, let's talk about end behavior first. So it's a positive odd degree. So I know that the end behavior, it's going to be going in opposite directions. So when x is positive, y is going positive, and it's probably going to be going down here, right? Now, it's a third degree, so how many x-intercepts could I have? As many as 3. And how many bends should I have? I should have as many as 2. So something like that would be a decent little sketch of what this could look like. Now, it doesn't guarantee that it has this many x-intercepts. We'll end up finding some ways to deal with that later to calculate the number of those. And technically, I could have told you that -1 is where it should have crossed the y-axis. But we at least have a general idea of what the shape of this looks like. And let's just do one more for fun. What if I have q of x equals negative x to the 6th plus 5. So we didn't do a 6th degree, but the characteristics are the same. So let's see, end behavior. It's even and upside down, right? So imagine that parabola. So it's even and upside down, so its end behavior should be pointing down. And I don't know what's going on between here, but it doesn't matter right now. So for end behavior, that's what we got. For number of x-intercepts, it has as many as 6. And for number of bends, it's 1 less than the degree, so it's got 5. So let's draw 5 bends. So 1, 2, 3, 4, 5, and I'd have a function kind of like this, right? And notice it has as many as 1, 2, 3, 4, 5, 6 x-intercepts. But it is actually possible that you could have a bend that doesn't go down the whole way, right? So it is possible to have fewer x-intercepts than that. Or it's possible that it could come down and just hit it once, and you could have things like that. But just right now, all we're concerned about is, do we at least know what this function kind of looks like? All right, and that's our goal. All right, so thanks for watching the video. Hope you guys have a great day.